In this video lecture, we will discuss uniqueness of measures and introduce the pi-lambda theorem. We'll present the discussion backwards, introducing the motivation when we're trying to study, for instance, uniqueness of measures, and this will motivate the definition of pi systems and lambda systems. And then in the second part of this video lecture, we move to the pi-lambda theorem and finally use it back to prove questions about uniqueness of measures. We'll start with some motivation for the definition of pi systems and lambda systems. Recall from previous lecture that we defined through a theorem that stated existence and uniqueness of a measure m that is defined on the real line and which is able to measure any Borel set. And there is a unique measure that assigns to intervals what we would like to call the length of those intervals. And we call it the Lebesgue measure. The existence part will be addressed in the next video lecture. Today we're going to discuss uniqueness. So let us start discussing the question of uniqueness. What is uniqueness? We assume that two objects, let's call them mu and nu, two measures, we assume that they satisfy a certain property, and then we show that in the end they are the same object. This is uniqueness. And what are we trying to prove here? To say that they are the same object is to say that the measure mu of A equals the measure nu of A for every A in the sigma algebra. Now, when we're trying to prove that something holds for every A in a sigma algebra, very often a good strategy is the following. We define the class of sets A that have this property. What is the property? That is exactly that mu of A equals nu of A. And we show that this class, in fact, has the entire sigma algebra F. Now, if we'll test whether A is in this class, meaning if we're going to test this equality for every single set in the sigma algebra, this is not realistic and overkilling. This is really very hard. Let's try a smarter approach and study the structure that this set D may have. If we knew beforehand that D was a sigma algebra, then all we have to do is to show that the sigma algebra coincides with F, and for that it is enough to show that D contains a class C, and that class can be much smaller, so that this class C generates the sigma algebra F, in the sense that sigma of C equal F. But we don't know that. We don't know whether D is a sigma algebra. However, it is clear that D has some structure. And let me discuss what this structure is. D is closed under complements. Well, at least if we assume that the measure of omega is finite and is the same for both mu and nu. And it is also closed under countable disjoint unions. And we can say that just from the basic properties of measures. However, this being closed under complements and countable disjoint unions does not yet mean that the measure that this class D is a sigma algebra, because there's no way to guarantee very easily that D is closed under intersections. So there is this bit of structure that is missing in principle from this class D that has to be given somehow. Now this motivates us to define two types of classes of sets which together encompass the structure that a sigma algebra has. The first is a very simple requirement. This is requiring very little structure about a class, which is we call a class a pi system if this class is closed under intersections. And closed, of course, just means if A and B are any two sets in the class C, then their intersection is also in C. And now, referring back to the previous slide, where we had a class D which naturally satisfied the property of being closed under complement and countable disjoint union, we define a lambda system to be exactly a collection of subsets of a given sample space, such that the entire sample space is a member of this collection. The collection is closed under complement and it's closed under countable disjoint unions. And so this class that we defined before, let me call this the coincidence class. That's the class where of sets such that mu of A and nu of A are equal. So here's a proposition. It says this class is a lambda system under this assumption here that the set has a finite measure for both mu and nu and they are the same measure. Let's skip the proof of that proposition and also of the missing piece that allows us to connect pi systems and lambda systems. Let's state this general theorem here to conclude this first part of this video lecture. It says that if mu and nu were two measures on some space and they assign the same measure to every set on a class C, which is closed under intersections, that's a very mild assumption on the class, but still with some assumption, it must have this level of structure. And here's a technical assumption, which is important. Suppose that we have sets of finite measure that are in this class. Okay, that's a class where they coincide. And this sets with finite measure, maybe they are all finite, but they're increasing, and they're increasing to infinity, it's okay. But the union of these increasing collection of sets is the entire space. Under this assumption, we can conclude that the two measures coincide not only on this class C, but on the whole sigma algebra generated by C. As a corollary of this theorem, we can prove that the Lebesgue measure is indeed unique. And how can we prove that? Well, first, what the theorem is saying is that there is a unique measure such that it assigns to closed intervals the length of those intervals. And the proof would be the following. In order to use the theorem, well, we need to provide some class C that's required in the theorem, which is closed under intersections. And in the proof, here we are providing a class. It's just the class of finite closed intervals. It is indeed closed under intersection. Well, it also requires that within this class, we can find an increasing sequence that increases to the whole space. And here it is, intervals that go from -n to n. As we make larger and larger, this will end up covering the entire real line. And each one of them has a finite length. And therefore, we can conclude that these two measures must be the same for every set on the sigma algebra generated by this collection. Well, the sigma algebra generated by closed intervals is the entire collection of Borel sets, and this concludes the proof of the theorem.